Thanks to the committee for the opportunity for Withali Gold to make this presentation. It's a lovely event and fantastic to see everybody here. Dave and I, we're living the dream, exploring in the beautiful Wiradjuri country out there around a really interesting granite near the lovely little village of Withali in the central Lachlan. What happened there? Okay. It's tricky, isn't it? I'd like to acknowledge the farmers and the landholders for the wonderful access that we have and the relationships we have with them, and the Wiradjuri people whose traditional lands we're exploring on, and the local people make our stay so comfortable. We're a small team, Dave and I, but we tap into a great intellectual set of mates in Dave Champion, John Wilford, Yangbo Chan, Roger Skiro and Tom Harris for a range of skill sets that we're applying in our exploration. Special call out to you, Glenn, for supporting us with the portable XRF, and Joe from ALS for support in the labs, so in terms of logistics. Big call out to the Geological Survey of New South Wales. We couldn't do the work without you, and also a great thanks for the co-funding of the IP geophysics that I'll be showing. And to Geoscience Australia, again, your data is amazing too, and in answering all the questions. The people, the talent in the geological surveys is so good. So gold and granite. So why? Well, granites are commonly a direct source of energy, fluid and metal. We see that obviously in porphyry, epithermal and intrusion-related systems. But granites themselves, they can alter the physical and chemical properties of the rocks they intrude, commonly giving competency contrasts, which can be sites of brittle dilation, failure and dilation, and hence mineralisation. They themselves alter the regional stress field and can guide stress trajectories into focused areas, and we'll see an example of that at Withali. And they themselves, of course, structurally controlled at a range of scales, as is the gold. Now, the picture I've got up there is Vic Wall's thermal aureole gold model. It's I guess, a variant of the intrusion-related model, and commonly these intrusions are associated with structures, and particularly antiforms and anticlines. Domes are important. Is that correct? Doesn't work. Okay, so the central Lachlan is dominated by these late Silurian granites, S-type granites largely, reflecting a major crustal anatexis in the back arc to the system. Most of the plutons you'll notice from these map patterns are elongate in a north-north direction, but one of the unusual ones, which has been our focus, was attracted us to the area initially, was this Withali granite, which is an unusual circular shape. Much of the gold is adjacent to or within many of these granites. Let's look a little bit deeper and into the gravity data set. So there's some outlines of the outcrop of granites. We see deep batholithic roots in the gravity lows. And we see these interesting trends, this north-northwest trend. And at Withali, it's sort of an elbow in this big north-northwest trend coming up from Wagga. And it kicks off to the northeast and then trends up to the northwest and so on. So it's at an interesting intersection of major structures. And we also, in the gravity data, see these enigmatic northwest trending things that we've had a bit of a discussion about yesterday in terms of those transfer zones. So Withali sits there right at this intersection of three of these big regional trends. We've known for quite some time now about the connection, or at least the empirical association, between gold and deep magnetotellurics, these conductors in the lower crust. This is a map from around 40 kilometres depth of the 3D model generated by GA and GS New South Wales. And we see that the Withali area sits on a gradient in this deep conductor in the OSLAMP magnetotellurics. And again, it's interesting that that's that northwest trend, and we were also seeing that Lachlan transfer, so-called Lachlan transfer, is that northwest trend. So it's real. We're seeing it in gravity, we're seeing it in magnetotellurics. And Withali sits on the edge of one of these. So in terms of the regional geology, it's low relief, like a lot of the area, very limited outcrop, less than 5%, and what you get is usually pretty weathered and miserable. Most of the regional strike is this north-northwest, as we saw in the gravity. But around Withali, it's quite interesting. We see the strikes going east-northeast, and I'll try and explain why that's the case. The region is deeply weathered, and most of the area, particularly around where we're exploring, is residual. A little bit of transported cover in the west. This area will just lift off that little bit of cover. And we see the Withali granite, this circular granite in around here, and the gold deposits associated clustering around, particularly in this contact aureole. The oldest rocks in the area, the Wagga group, Ordovician, deposited and then deformed in the Benambrum around 440. And we see upright folds, thrusts. The Norai Fault was active at the time. That links back into the east to the Gilmore. And then we see this great sea of granites, the Withali in here, intruded around 427, at least there locally. What's really interesting about that is that was intruded at around 10 kilometres depth, and within 10 million years it was at the surface, and it was having the Rast trough. This is the Gurragong groups, Ural volcanics. We heard about those just now from Glenn, deposited unconformably on them. So there's been a huge amount of telescoping and uplift in this region. We then have, as I said, these volcanics deposited. They're flat-lying now. Then we have Tabaraban deformation, unconformity, and then the Kokopara, the late Devonian Kokopara group, sitting in here in the Norai syncline. You can sort of see that in the bit of the DEM, folded into a tight syncline. So they were deformed in the Canimblin around 360 million years ago. And that unconformity is dipping at 60 degrees. So it's really odd, this area. You've got an unconformity of 60 degrees here. This is pretty flat-lying, and the Ordovician sitting there vertically. So there's been a hell of a lot of strain partitioning in this region. And we think that the Withali granite is playing part of that. So let's again just strip the geology off and look a bit underneath. We see these big Benambrum folds, and I'm interested to know whether they're anticlines or synclines, and I'll show you what they are. The Withali granite... True, I can see it. Thanks, Karen. Wow, I've been pointing all the time. Good guess. Okay, thanks for that. We see these demag zones as well, and they tend to be bounded by these northeast trending structures. And as I said, the gold deposits are clustering, and now the mouse doesn't work when you've got a laser. Yeah, this is shite, isn't it? We've got this aureole around here in the gold deposits. Again, this northwest strike. So Dave took the beautiful GS New South Wales data, ran an inversion to 16 kilometres. We wanted to be able to model this and understand the 3D architecture, and I'll just run that little model. Can I do that? So what you see happening is those limbs on those folds are converging at depth. You see it up there in this, so they're clearly synclines. So you've got these two bunny ears synclines plunging to the southeast, and this major fault, what we've labelled the Withali fault, is basically faulting into the anticline. The Withali granite itself is split by that fault, and is obviously in placement is controlled along that structure. So this structure was Benambran age, late Silurian age, and as we come to the south, it bounds the Gurragong trough, the Rast trough to the south here. So it's, and we can also see the in the cross section the shapes of these. So that was a summary of what the Withali fault is doing. We also see in these deeper sections, this is about 3.5 kilometres, these northeast trending structures of these mag and demag zones and these boundaries, and they're important. So there's a lot of geological complexity being focused, particularly in this southern area and in and around Withali. So let's jump into the Uratha deposit, which is the one we've been working on mostly. It was discovered in around 1900, mined up until about 1937. It's sort of north, a little bit angled here. It strikes east-northeast, like all the trends I've been talking about. There are minor north-northwest trending strikes at faults that dissect the lode. Grades were humongous, up to 3 ounces per tonne, and very, very high silver. We can see that in the assays that were done at the time. Probably a bit small to see, but they were running 8 ounces of silver. And, so really outstanding values. And that's what the area looks like, the stopes and the shafts and so on. So there's a bit of legacy drill core. It was some of the previous tenement holders drilled, not in great shape, but we were able to sample that and then work out the vein paragenesis. And also any mapping, obviously, of anything that sticks out of the ground. So Ben Goscombe, we commissioned him, he's our co-author, has done an amazing job on defining the vein paragenesis. Those who know Ben, big thick report, and lots and lots of detail. I won't go through all of that, other than to say that we've got this hornfels that's associated with the contact metamorphism with the granite, the Withali granite. And then we go into a phase of, or a number of veins that are dominated by pyrite, quartz, tourmaline, carbonate, muscovite, and so on. What we're seeing is a progressive cooling of that contact aureole. It's clearly a magmatic system and it's associated with gold. That's where most of our gold is. Okay, so it's an intrusion-related system. And that's not surprising given what Peter Downs was saying back in 2004 in terms of the sulfur isotopes, 1.9 and 2.1 per mil for pyrite and arseniopyrite. So clearly a magmatic component. But Ben's also been able to show that those late veins, what he called E12, are these sort of milky quartz, dogtooth, open space. And that's definitely in there, and that's probably reflecting a Canimblin orogenic system, overprinting on the top. We have high temperatures, so the PT conditions 500 degrees and around 10 kilometres depth. So a little bit about some of the mineralisation. Here's the granite, that's the causative granite that are in dikes and so on in the drill core. It's not exposed to the surface, so it's only from that drill core. Some of these E4 veins and some of the mineralogy here, tourmaline, pyrite, muscovite, rutile, apatite, probably monazite, arsenopyrite, galena, sphalerite, etc. A couple more variants of this main mineralising event. It's what he called E5 and E8. I won't just read that. And then these are these late E12 Canimblin-aged quartz, pyrite and gold veins. So I wanted to know, well, we've got this causative granite in there, it's not been mapped, so which one is it? The two candidates would be, so here's the what we call the Uratha granite, and we plotted it up. Thanks, Joe, for helping with the geochem, and Dave Champion, who generated these plots and interpreted it for me. So the two candidates are either the Schillersley granite, which is part of that, intrudes into the Gurragon group in the Ras Trough, and that's an A-type, and clearly it plots up there. This doesn't plot anywhere near that. It plots down there where the Withali granite plots, so a more mafic version of the Withali granite. So it's 427. Now remember, the extension direction at that time was east-northeast, and yet we've got veins that are striking parallel to that east-northeast. How the hell does that work? Okay, so maybe we've got an explanation here. In extension, normal faults don't go forever, and commonly movement is transferred from one fault to another across what we call an accommodation zone. So I've taken this diagram, flipped it to try and sort of make it fit the orientation of the structures we see. So what we think is this Withali fault was active in the emplacement of the Withali granite. It came in, became locked, movement was taken to the west, and we get a relay ramp developed along that southern margin, giving us that northwest directed extension. So that gives us that northwest directed extension at that time, at least locally. So where's the gold? These are from the slabs that we've made from the old mullock heaps, and we're running about 36 grams, or up to 36 grams per tonne. We sampled a range of the vein types, E4 to E12. We slabbed them, polished them, thin-sectioned them, and we then put them through that a micro-XRF scanner. So this was Ben Wade at the University of Adelaide. This particular vein, just one example, we've done them all, but was running about 22 grams. The gold is incredibly fine. You can see it. It's in pyrite, arsenopyrite, and free in the quartz, but there's a lot more gold in that sample, obviously, than's visible. And you've got to remember that here's 5 millimetres in terms of scale, so these aren't little thin sections, these are big slabs. There's a lot more gold that's finer than the 100 micron beam size of that machine. What we do know, though, is that arsenic, gold, lead and zinc are strongly associated, as are sulfides. So this gives us a good clue about how we can explore for more of this, for gold, that is. The original drilling as well, a correlation matrix of gold. Gold clearly links with silver, as we well know, arsenic and pyrite and those base metals. So arsenic and gold are clearly coupled, so that gives us a good clue. We can use portable XRF soil geochemistry, if we understand our regolith, which we do, and we can use electrical geophysics for the sulfides. So let's just zoom in. Here's the bottom of our EL. Withali, the town, is in here. This is where the Uratha deposit, the existing drilling, just in underneath the existing deposit. Large areas that just have not been touched with the drill hole ever. Okay. One thing that we've seen very little of in the conference is LiDAR. And of course, the LiDAR exists for most of New South Wales. And Dave stitched together the entire Zone 55 of beautiful LiDAR. And it's amazing what you can see in the landscape features are reflecting of the deeper geology. And we see these east-northeast really subtle ridges, which when you're out in the landscape, really struggle to see them. It looks flat as, but amazing structure that's running through there, and even the offsets on them that you can see are reflecting the deeper structure, and you'll see that later. We also did some stream sediment geochemistry. We know there's gold shedding off this. We wanted to understand our regolith. I had John Wilford come in and help me look at this, and it's a residual environment. We can see that in the dams. So again, we can just basically point the portable XRF at the soil and look for arsenic, which is what we'll do. We flew 25-metre aero mag over this area in through here, and Dave's done 3D modelling of this. We've used it obviously for structural interpretation, mapping these demagnetization zones, and also stripping off the paleo channels that we see, those maghemite dendritic patterns, so we can see the deeper structure underneath. So this is our exploration corridor where we've been focused. So this is coming in. This is the Uratha line of working, slightly elevated rise in there. We did some orientation for our portable XRF in terms of understanding the soils. We worked out a workflow that we could collect 10 to 20 centimetre depth soil, every 30 metre spacing, around 150 metre line spacing, and we would find the anomalies. And so that's what we did, and here's the results. Again, up very high over the known mineralisation, and then these very interesting anomalies, east, west and south of known mineralisation and to the north of mineralisation. So basically, none of this has been drilled, and this is all good to go. We also wanted to know that it's all very well saying in the ores that we get gold and arsenic coupled, but are the soils really do they truly link to the gold? So we did a bit of an experiment. We put low arsenic numbers soils into the lab at ALS, and high arsenic numbers, and of course there's a very strong relationship. And this is ppm gold, not ppb. So there's a lot of gold in those soils. And it's open, east, west, north and south. So again, grateful to the GS New South Wales government for the co-funding for the IP. We did 5 north-south deep dipole lines and about a 3 square kilometre gradient array. Dave ran this and did the in-house processing and modelling. I'll show you some of just these areas. This is this presentation of the data. Dave is a gun at generating lots and lots of images. These were the ones I'll show you, the chargeability and resistivity. Let's look at resistivity first. So that shows the mineralisation. Here's the Uratha line of workings. I've also got those DEM little interpretations from the LiDAR on top as well. It's a strong electrical resistor. We're interpreting that as the quartz associated with the alteration, and it's reflected alteration at depth. They also correspond to these subtle DEM landscape features. So these are also topographically resistant as well as electrically resistant. And we know from the magnetics, and the high-resolution magnetics, that the paleo channels deviate around these. So it's been persistent in at least persistent as landscape features since at least the Miocene, and obviously before that. Let's look at the chargeability. We see that the mineralisation is coincident with these really, really chargeable anomalies. It's not surprising given the amount of sulphides in the system. And we got anomalies all the way to the east. We're just starting to see some to the south and to the north. And it's again interesting to see those subtle landscape features in the DEM reflected in the IP. So I think the LiDAR is a data set. Certainly works for us beautifully here, and be interested to know if it works elsewhere as first pass. Let's just drop the arsenic from soils onto the chargeability, and again we see that great relationship between often the gradients in these chargeability and the portable XRF soils. We, like Glenn, the portable XRF is a fantastic screening tool. Again, open, east, west, and south. So we did these 5 dipole traverses, these 4 tightly in, they're 100 metres apart over the deposit and north and south. We couldn't really go much further with our studies because of the land access issues are down here. So we're sort of limited a little bit to what we've got there, although we've sorted out our land access now, thank goodness. I'm just going to focus in on this central area. Just cut that back and show you those sections. So there are here we go, the chargeability and the resistivity. And I'll zoom in on just around the mine. And here we see the sections, so south, north, and this is this section. You can see the existing drilling and the existing mine, what was mined out, that's down to about 100 metres depth. And all the drilling's missed all these new IP targets that we've got right adjacent to the mine, just in here. And we see the magnetic bodies down here in the green. So you can see this major, this sort of magnetic gradient as well. So we've got this coincidence of a magnetic edge, the chargeability and the resistivity. So we've got these great targets at depth, and that's just in this little part. So we've got all of this to play with. Dave's taken these sections and put them into 3D software and done a pseudo 3D model, and then we've done depth slices of those. So we're just going down the levels. And I'll just pop this in here, so there are those levels, and I've just picked a few. So this is 20 metre depth, 40 metre depth, 70, 110. You can see here the gradient array contours. Here are the silhouettes of the chargeable, the chargeability, and the coincidence of that, and the drilling in and around that. So that's great, they found what we already knew. But what they did miss was, of course, all these guys coming out here and starting to emerge in here. And that's very shallow, only 70 metres below the surface, only 100 metres below, and going deeper, and so on. So these are untested, these are some of our high priority targets, and they're right in that zone there. So that's my final comments. I think that the Withali area's got excellent potential for new gold discovery, both right near the deposit itself and also further afield. The region's seen very limited exploration and very little drilling. We see the region it's this unusual round circular shaped body. It's probably the convergence of a lot of deep structures as well as more local scale structures into microstructures converging and focusing in on the Withali area. This granite itself was intimately associated with the first stage of mineralisation. And once in place, guided the local stress field and later orogenic, probably Canimblin mineralisation over the top. We've developed a workflow that we think which works for us. Been quite a lot of trial and error, but that's exploration, isn't it? Which we would like to think we're glad to share it with you and might be applicable to you elsewhere in the origin, exploring around granites or in the Tasmanides in general. We have our targets. But we just want to do a little bit more IP and before we drill, really tighten them up. And we're trying to use science for discovery, and this is about discovery, obviously. But it's the ultimate truth machine, the drill, that will really test our hypotheses. So watch this space. We hope to be back in 2 years' time with a story like Glenn's of a great discovery. And the video up there was a drone. I borrowed my son's drone, and I'm a lousy pilot. Had a bit of a fly of it, and that's just flying over the line of load. You can see the shafts there, and just out that country, flat, easy country. It's all residual. It's cropping. It's great, and we've got great landowners, and it's all upbeat from here. So thanks for your time, and thanks for the opportunity to speak. And it's nearly tea time.